state is when the properties does not change with respect to time, and unsteady state it will change with respect to time. So here is a similarity fundamental principle. Both method follows the same mathematical models, that is conservation of mass, energy, and momentum, to describe the system or to give us what is happening in the system, the behavior. System representation, it will use differential equations, and the objective. The both objective is to predict the system behavior. So now the differences, the time dependency. Like I said, steady state does not change with respect to time. So it assumes the state system has reached equilibrium and does not change with respect to time. Whereas this simulates the system behavior as it evolves over the time. Characteristic describes the system where input and output remains the constant, meaning whatever the mass is entering the system should leave the system, whatever the energy is entering the system should leave the system. Energy, if we are talking about heat transfer, then it is typically simpler because the behavior is not changing with respect to time. It is a much more complex. It requires less computational time because it is simpler in complexity. It requires more uh, computational resources due to time stepping calculation. More on that further. What is time step calculation? So this is some examples where we would use transient state and steady state simulation. So the summary, steady state is not suitable when the flow or the condition changing over time, such as for turbulent flow, pulsating flow, or the cases in which the boundary condition, boundary condition is not is changing. Boundary condition is changing. But do keep remember that in CFD analysis, this is particularly for CFD analysis I am discussing on, even though it is true for structural analysis, static structural, transient structural, but I am focusing on computational fluid dynamics. So the boundary condition in CFD, we give fixed boundary condition. Let's say at inlet velocity is 5 meters per second, and we do not change that uh, in the simulation, during the simulation, during the calculation period. So the boundary condition is fixed, but in the real case scenario, the boundary condition is never fixed. It changes as due to the various reason, atmospheric changes and the temperature changes and all those things. But in CFD analysis, we give fixed boundary conditions. For most, yeah, we give fixed condition. Steady state simulation is appropriate when you're dealing with, yeah, uh, where the fluid has reached equilibrium or transient effect are not significant. So what is mean by that is you do not want the, to know how the dynamic behavior is happening in the system during the simulation or after the simulation in results. So you only wanted to see what is the pressure at some location, what is the velocity at some location, or what is the velocity along a x direction or along a y direction. So, like I said, steady state will only account for changes in pressure, where velocity, temperature, and so on with respect to space, not with respect to time. So if you wanted to only your main goal or main focus is how the velocity is changing from inlet region to the outlet region, how the velocity is changing with respect to space, you you can opt for steady state simulation. So that would give you less computational solving time and less complexity, simpler complexity, and solving time would be less. So that is, so when we opt for unsteady state simulation for CFD analysis, ANSYS Fluent calls this unsteady state simulation as transient state simulation. So I'll use transient state simulation. So when to choose transient state simulation? So when you wanted to see the behavior, like behavior of fluid like properties like velocity, pressure, temperature, and so on with respect to space as well as with respect to time. You wanted to see how the velocity has changed from 0 seconds to so and so seconds, let's say for 5 seconds, how the velocity has changed. You wanted to plot a graph, then you would opt for transient state. Like for in case of drone propeller is rotating at 1600 rpm, let's say 1600 rpm, and you wanted to see how the thrust is generating from, let's say, from initial condition from 0 seconds to after 12 seconds. So what is the thrust is generating in between that, how the thrust value is changing. You wanted to study that, you go for transient state. Or you just wanted to see how this if we are rotating drone propeller at 1600 rpm, how would that 1600 rpm rotation would give you the thrust not with respect to time, but with respect to space. How that thrust force is uh, generating generated due to the drone propeller with respect to space, then you would go for steady state. But when you wanted for when you wanted for space as well as time, with respect to time and with respect to space, you go for transient state. But it comes at a cost of higher computational resource, higher computational solving time, and much complexity. So here it says when you need to study time dependent behavior like wave propagation or heat transfer in system that changes over time. Yeah, so now let's discuss on this is steady state in ANSYS Flint. So assuming that we have given everything geometry from meshing to boundary condition, and at last this is the last where you would set the hit the calculate button and you would start your steady state simulation or unsteady state simulation or transient state simulation. So before that, steady state simulation will ask you for one parameter, that is number of iteration. So here for most cases 1500 iteration would be sufficient, or for complex problems 3000 would be okay. So what is this meant by number of iteration? So like I said, both solves the mathematical model of conservation of mass, conservation of energy and momentum. Those equation would be solved over 100 times because here it is mentioned 100. So conservation of mass is being solved by the ANSYS solver for 100 times. So why 100 times? The larger the repetition of calculation, the more accurate your simulation will be. So if you hit for 1500, the calculation would be those equations would be calculated for 1500 times. So higher the number, higher the accuracy. So here for steady state, the only parameter is iterations, and that has to be 1500 or 3000 for complex problems. You can also use more than that. Now, when you go for transient simulation, or transient simulation is also known as unsteady state simulation, it will ask you for three parameters: time step and number of time step and number of iteration. Here, the time step would be at what time you wanted to calculate your those fundamental mathematical model equations, at what time you wanted to calculate those. Here the time step has written as 0.02 seconds, so which means, so this is t equals to 0 seconds, that is your initial uh, conditions at the initial 0 second, and this is your 0.02 seconds, so which means at here at particularly at 0.02 second, your three equation would be solved. So and then again another after another 0.02 seconds, same equation would be solved. So in between this, so from 0 to 0.2 seconds, in between those, in between that, there won't be any calculation for those mathematical models. There won't be any calculation. So here the number of time step is 1200. So 1200 intervals. So 0, 1, 2, 3 like that 1200. So if you multiply, time step is 0.02 seconds and number of time step is 1200. If you multiply both, you will get 24 seconds. That is uh, flow time, or that is the number of seconds you are simulating your system for. So so remember that this 24-second does not correspond to your solving time, computational solving time. It is much higher than that. It is simply you're simulating your solution for only 24 seconds. So you only have 24 seconds of relevant data at an interval of 0.02 seconds in your solution part. In the result, you can see only what has happened at 0.02 seconds, what has happened at 0.04 seconds, and what has happened at 0.06 seconds. If you wanted to see for 0. Let's say 1 second, you won't have the detail result in your simulation. So like that, you have 24 seconds of data at every interval of 0.02 seconds. So this is the first parameter, time step size and number of time step size. Like I explained what is the significant of this, and this is the time stepping calculation. This is called the time stepping calculation, which I have highlighted here. Requires more computational resources due to the need for time stepping calculation. That is the time stepping calculation. Now this is the one, this is the two. Multiplying these two would give you 24 seconds or X number of seconds you wanted to simulate your solution or problem for. So now number of iteration. The number of iteration will also be in the transient simulation. So, but here in the transient simulation there is a catch. You do not need to give higher value of what's say this iterations value because uh, see it is 0 seconds and it is 0.02 seconds. So you are looking for what has happened after 0.02 seconds. So nothing major changes has happened, only significant changes has happened. So for that, to give you enough accuracy to get you at convergence point below 30, number of iteration would be sufficient. You do not need to go for 1500 3000 iteration. Even for more complex problem you do not need to go for 1500 3000 iteration. 30, in between 30 to 50 would be sufficient. Those for 0.04 seconds, from 0.02 seconds to 0.04 seconds, nothing that majorly has changed. So that is the reason we give less number of iteration. And so ANSYS recommends for using time step value in the order of 10 to the power of minus 5 or 10 to the power of minus 6. So that means the each interval is so close that you don't need to go for higher number of iteration. You can go for lower number of iteration, because even if you go for a higher number of iteration, nothing would happen. Your simulation would get convergence at for this only for this interval. Your convergence will reach faster for then again for this iteration. Let's say you have given 30 number of iteration, 30 calculations would be done for each mathematical model, and you will reach convergence in somewhere in between 0 to 30. Same for this one, and same for this one, and same for this one, and so on for 200. So do not increase your iteration value in a large amount. If you wanted to tweak something, change these two parameters. You can decrease this parameter. The time step also, the one thing, the time step should not be larger value. Let's say 10 seconds. Let's say t equals to 0 second, and the next interval you're calculating for is 10 seconds. In between that 10 seconds, the major changes has already done. Major changes has already been changed. Those things already happened, but your simulation did not account that for, because you have simulated your simulation start at 0 seconds and you calculated your simulation at 10 seconds, and then you calculated your calculation has happened after another 10 seconds, that is 20 seconds, like that. In in between that you have 10 seconds of time. In that time, uh, major dynamic changes will happen and you miss those part. That's the reason, do not take higher time step, take smaller value, like here in this case 0.02 second, and if you are not satisfied with that, go even lower than that. You can increase number of time step. So now graph that has generated in during CFD analysis. So this is drag coefficient on the vertical axis, and this is the flow time. This flow time is this total number of simulation you are simulating the simulation problem for, that is 24 seconds. Here some other seconds, like so on so on so on, at the each interval of 0.02 seconds, 0.02 0.02 seconds, like that. See, you only have the relevant data what is happened 0.2 0.2. So here, yeah, if you would have taken smaller value, let's say you're plotting a graph, your graph would have been smoother. If you taken the smaller value, the graph would have been more smoother. Let's say if you have taken 10, let's say this is 0 and here somewhere here is 10, you would have a straight line. Much of the details has been already gone out of your results, out of your simulation. So yeah, okay. The point is here. Let's see how the drag coefficient is changing. So at 0 seconds, it started from 0 and it started slowly increasing, which means it is the drag coefficient is changing with respect to time. As the time is increasing, as the time is changing, the drag coefficient is also changing. But at this point, let's say at somewhere 0.05 seconds, the drag coefficient did not change that significantly as here. It has somewhat is a straight line. So we can say that the drag coefficient is not changing significantly, so from this point to onwards, which means at this but for this particular simulation, even though you have done transient simulation, we have reached a steady state, and that is when you need to stop your simulation. For transient simulation, you will stop your simulation where your property of a particular thing, whatever you are interested for the properties. Like here I have shown drag coefficient. If you are interested for velocity, if you are interested in pressure, so whatever that is up to uh, one's choice. So whenever you see that property is constant over time, that is when know that your simulation has reached steady state, which means the property won't change. Now it will be a constant over any number of seconds, which means if you even furtherly calculate your simulation, you go on extending the simulation, there won't be any changes in your result part. So that is when you need to stop your simulation. I could have stopped right exactly 0.08 seconds or 0.1 second or 0.12 seconds or 0.14 seconds. I do not need to have go through 24 seconds. I stopped at 0.14 seconds because all those remaining seconds would be waste of my time and waste of simulation and the waste of computational resources and solving time. So this is steady state and unsteady state simulation. Thank you very much. If you like my content, please subscribe our channel.